Welcome to lectures and topics. This is part 2 in ultrasound lecture. After we covered in part 1 how ultrasound is produced and how to propagate, and what does effective radiating area means, and beam non-uniformity ratio means, and what is the differences between 1 MHz and 3 MHz, and that intensity is in direct relationship with cavitation. So in acute stage of lesions, we use low intensity because we don't need to do a large cavitation at the lesion site, because angiogenesis and fibrogenesis is an immature tissue, so which the cavitation may harm the tissue. Today, we're going to explain how to use these parameters. In the parameters of ultrasound, there are two schools. The first school is the complex one, and the second school is the simplified one. In therapeutic modalities, art and science book, states that the accuracy of parameters is the main factor in obtaining optimal therapeutic effect of ultrasound. So today we're going to explain the complex one of obtaining parameters of ultrasound. In the simplified one, I will put a link in the description which cover the simplified one. Before understanding how to use the parameters, we must first know what is the differences between light and sound. Light doesn't need medium to propagate because it depends on its particles, while sound needs medium to propagate through, as we explained in part 1. Since light doesn't depend on any medium, so it has constant velocity. While in sound, because it depends on medium, and there are different mediums as gas, liquid, and solid, so velocity is varies according to the medium which is propagated through. Velocity is in direct relationship with the stiffness of the medium and density of the medium. To understand this, let's say we have a square with the same size. One is filled with gas, and the other filled with liquids. And the third is filled with solids. If you notice now, despite the square have the same size as the three mediums, but in gas it contains a few particles because gas atoms and molecules have low stiffness, and stiffness means the attraction between the atoms and molecules. Since it has low stiffness, the atoms and molecules are far from each other. While in liquid, because it has high stiffness comparing to gas, so it contains high molecules and atoms. Because as stiffness increases, the atoms become close to each other, so there's going to be another space empty which is going to be filled with other atoms, which makes this square is filled with more atoms than gas. While solid, because it has highest stiffness, so it contains the largest number of atoms in the square comparing to the others. So stiffness is the degree of attraction between atoms and molecules. Density is mass per unit volume, since volume is constant in the three squares, but due to stiffness here is very high in solid, so the square occupy more and more atoms than liquid and gas, to increase the mass of the square. While in gas, because it has less stiffness, so atoms are very far from each other, so these atoms lie in the square, So the mass is low, which makes the density of gas is very low. So according to this, since velocity is in direct relationship with stiffness and density, solid has higher velocity than liquid, and liquid has higher velocity than gas. There is a term called CM, which means specific heat capacity. Specific heat capacity is the amount of energy needed to raise the temperature of 1 gram of any substance 1 Celsius. So let's say we have also 3 squares with 3 different mediums or materials. The amount of energy needed to increase the temperature of a solid by 1 Celsius gonna be huge compared to liquid compared to gas, because solid has very large amount of atoms and molecules, so I need a larger amount of energy to increase the energy of all these atoms. While in gas, because it has less amount of atoms and molecules, so I need a less amount of energy to raise the temperature of the molecules of the square by 1 Celsius. So the point from this is to understand that different materials have different specific heat of capacity. So if I want to increase the temperature of muscle by ultrasound, it will be different in parameters if I'm using to increase the temperature of skin by 1 Celsius, because each material has its own specific heat capacity. So now let's say that we have a sound wave is propagating through this square. Let's take a closer look. If here is a sound wave and here is atoms and molecules of any medium. When sound wave is propagating through this material, atoms and molecules, since sound wave is a mechanical wave and also a pressure wave as we discussed in part 1, so we want to make a motion as these atoms and molecules. We'll find that these atoms and molecules will resist this motion. We call this law of inertia or inertia, which means that it is the tendency of any object to maintain its state of motion or rest. Since we have different materials and different mediums, so we have different inertia. So inertia and the degree of resistance of these atoms and molecules depend on the medium. In physics, we call this resistance by inertia, but in acoustic, we call it acoustic impedance. So acoustic impedance, it is the resistance of the atoms and molecules of any medium to resist the motion of the sound wave. Acoustic impedance equation is Z equal to density and velocity. So this means that since solid has higher density than liquid and gas and higher velocity than liquid and gas, so it has high acoustic impedance too. And the liquid has a high acoustic impedance than gas, which is the resistance of the atoms and molecules of liquid to resist the motion of the sound wave. So a question now. If liquid has higher acoustic impedance than gas, so why in ultrasound we use liquid as coupling medium, not using gas? The answer of this problem is acoustic impedance interference. Acoustic impedance interference means when the sound wave propagating between different materials. Let's say this is solid and this is gas. When sound wave propagating between different materials, so let's say we have now a sound wave propagating in this direction. First, sound wave will propagate through the solid and will have a resistance from the solid, which is acoustic impedance to the motion of its molecules as sound wave is propagating through it. Then, when the sound wave is propagating through the solid, it will reach to a distance where the atoms of solid and gas meeting each other. We call this line by acoustic impedance interference, which means that it is a line separating between different mediums with different acoustic impedance and different densities. The larger the difference between these two mediums will cause a large acoustic impedance difference. The larger this acoustic impedance difference, the more the sound waves will be reflected and the other will be refracted inside the gas. So, to avoid the point of acoustic impedance interference, we have to use different materials that have the same similarity in acoustic impedance and density. Because if you notice, solid is high acoustic impedance and gas is very, very low in acoustic impedance. So to treat this problem, which is acoustic impedance interference, we use liquid. Since the ultrasound transducer surface is formed of stainless steel, so if I'm using gas, the amount of reflection due to acoustic impedance interference is going to be 90%. While if I'm using liquid, the amount of reflection is going to be 0. So this means that I'm sacrificed by some of sound energy by using liquid than using gas, because liquid has higher acoustic impedance than gas, to avoid the greatest amount of reflection and refractions that gonna be happening when the sound wave gonna be propagated from the stainless steel transducer to the gas, or from the gas to the skin. So I'm using here, during ultrasound therapy, liquid or gel. So to avoid this point, which is acoustic impedance interference. Now let's talk about how to use the parameters after understanding these scientific terms now. Let's remove this part. If this is the transducer head, and this is the skin, this is subcutaneous tissue, this is the muscle, and finally bone. So bone, muscle, subcutaneous tissue, and skin. So this is a transducer head. Now if I'm treating a lesion at the muscle here, so the sound wave must propagate through all three different mediums to reach to the muscle. So what are the obstacles? That gonna face this sound wave and how to treat it. First is the acoustic impedance interference between the transducer head and the air, and treating it by using a liquid or a material that has acoustic impedance close to the skin and the transducer head. So we use here a jelly to avoid loss of sound wave energy at this area. So we use here jelly. Second is the acoustic impedance interference between different materials will cause some of reflection to sound wave. The acoustic impedance interference between the liquid I'm using and the skin is 0.1% of reflection will happen here. And between skin and subcutaneous tissue, 0.9% of reflection will happen. Between subcutaneous tissue and muscle, 0.8 of reflection is going to happen. Between muscle and bone, 34.5 amount of reflection. So the first problem we're going to face the sound waves during its propagation towards the lesion is reflection. Clinical note: you may hear that patient may complain from dull aching preosteal pain during the session. Preosteal pain during the session. The reason for this large amount of reflection which occur at the level of the muscle bone interference. When sound waves is propagating towards bone, 34.5 will be reflected, which is a very large amount. When the coming sound wave is coming to the bone, say here is the coming wave, it will be summoned with the reflected wave. So at this level here, the amount of sound wave is very huge, which will cause heating at this point, this is the reason for dull aching preosteal pain during therapy. So the key to solve this problem is by doing rotation. One of references mentions that while doing rotation, you must rotate in different directions, not only in one direction, because by doing in one direction you will cause rotatory reflection. Now, after we know that the first obstacle that gonna face sound wave to reach its lesion is reflection, the second problem is gonna be reflection. Reflection also occurs due to differences between density. When sound waves propagate between different densities, some of it will reflect. To minimize the amount of reflection, when we're doing ultrasound therapy, the transducer head must be in perpendicular to the treating area. Final problem is absorption. Absorption means that when sound wave is propagating through medium, for example skin and subcutaneous tissue to reach to the muscle, some of its energy will be absorbed by the skin and will not be transmitted to the next medium. It's also okay with subcutaneous tissue. Each medium the sound wave will propagate through it will cause absorption of subcutaneous tissue. Since I told you in the first part that absorption depends on the frequencies that I use, since 1 MHz has high diffraction and divergence, so it can preserve its energy. This means that, for example, if I am having 1 MHz and 3 MHz waves propagating through skin, 3 MHz will lose most of its energy to the skin, while 1 MHz will preserve most of its energy through skin. This means that despite the skin is constant material, but it behaves differently with 1 MHz and 3 MHz. And the reason for this is the diffraction which 1 MHz has. So absorption. So absorption is different with 1 megahertz and 3 megahertz. In 1 megahertz, skin absorption is 0.62, while in 3 megahertz it is 1.62, and subcutaneous fat 0.14 and 1.42 is 1 megahertz, and with muscle it is 0.75 and 2.28 with 3 megahertz, and finally bone it is 0.62 percentage 1.86. We call this by absorption coefficient. Finally, we call all these obstacles that gonna face the sound waves and would make the sound lose some of its energy by attenuation coefficient. Which means that it is a measure of the energy loss when sound propagates in medium. So since absorption is one with the obstacles, and since absorption is in direct relation with the frequency, so also attenuation coefficient will be in direct relation with frequency. So I have two forms of attenuation coefficient: 1 megahertz attenuation coefficient and 3 megahertz attenuation coefficient. In skin with 1 megahertz it is 0.326, and with subcutaneous tissue it is 0.07, and with muscle it is 0.101. To get the 3 megahertz attenuation coefficient, must multiply by 3. Now, if I'm using now an intensity to treat an acute lesion of the muscle, since there is energy being absorbed from sound wave, so the intensity as the transducer head and I put on the device, which is IO, it will be always smaller than the amount of intensity that gonna be at the lesion site. So I have to know how much the medium which is between the transducer and the target tissue will absorb of energy. And to get this, we use this equation. First, to get the intensity at the device, it will be intensity at the distance E minus 2 by A by D. This means that if I want to calculate the intensity at the ultrasound device, I must know first what the intensity that I need at the lesion site, and this depends on the stage of the lesion. If it is acute lesion, I can choose from 0.1 to 0.3 watt per centimeter square at the lesion site. If it is subacute lesion, I can take from 0.2 to 0.5 watt per centimeter square. And in chronic lesion, I can choose from 0.5 to 1 centimeter square. Let's say now we have now an acute lesion here. So I will take 0.2. So the intensity as a distance is going to be 0.2 watt per centimeter square. E is an exponential, which is equal to 2.70, which is equal to 2.72 minus 2 by A, which is the attenuation coefficient of the medium and material above the target tissue. In this case, I'm treating the muscle, so the medium which is above the muscle and the layer which is medium which is above the muscle is the subcutaneous tissue in the skin. So first I have to measure the distance of the subcutaneous tissue and the skin, I can measure the distance of subcutaneous tissue by using skin caliper. The skin, which it's vary in the body, with 0.5 millimeter square in general. So, for example, here the distance may be 2 centimeters. 2 centimeters is formed by how much skin and how much subcutaneous tissue. And finally, I have to know the attenuation coefficient of these layers. And since attenuation coefficient depends on frequency that I use, since this problem is at 2 centimeter depth, so the optimal therapeutic frequency is 3 megahertz. So I choose 3 megahertz, so I have to get the attenuation coefficient of 3 megahertz of the skin and subcutaneous tissue. Let's say now we have 2 centimeter, 1 centimeter skin and 1 centimeter subcutaneous tissue. So this distance is 2 centimeter. So I make a bracket 1 centimeter by the attenuation coefficient of the skin at 3 megahertz, which is going to be 0.3263 plus 1 centimeter, and you get the attenuation coefficient of subcutaneous tissue, which is 3 pi 0.7, 3 pi 0.07. And write this equation in the calculator, and your intensity at the transducer head and this device will appear to you. And this is the intensity that you're gonna write on the ultrasound device. Let's try it on calculator. 0.02, 2.72, 2.72 minus 2 by 1 by 0.326 by 3 plus 1 by 3 by 0.07 . The intensity that you need is 0.21. Approximation 1 per centimeter squared. Now, after understand how to use intensity, let's know how to get time. So let's remove this equation from here. After understanding now how to calculate intensity at transducer head and doing ultrasound device by using the equation of I initial, which is I at the transducer head equal I at the lesion site over E, which is exponential, minus 2 by E by D, which is standing for attenuation coefficient. To calculate the time of the session, there are 3 factors affecting the time of the session. First factor is time for exposure, ultrasound to the lesion site by relationship of effective radiating area to lesion area, and finally duty factor. To calculate the time of exposure of ultrasound to the lesion site, we use the following equation, which says that time of exposure to the lesion site will equal to density by specific heat capacity by temperature over 2 by E by I. The result would be in second. You have to divide this by 60 to get the result in minutes. The units in this equation is very important. Density is standing for the density of the target tissue that you are treating. The density must be in gram per centimeter cube to put it in this equation. Specific heat capacity is the amount of energy needed to elevate the temperature of the target tissue by 1 Celsius. I'll give you a link in the description containing specific heat capacity of different body tissues, but the unit in the link is in joule per kilogram per Celsius. So you must divide this by 1000 to get joule per gram per Celsius. T is standing for the temperature. I told you that ultrasound has a thermal and non-thermal effect. If you want to use the thermal effect of ultrasound, you may substitute T here by 1 Celsius or 2 Celsius or 3 to 4 Celsius. 1 Celsius elevation of temperature will cause increase in basal metabolic rate, while 2 Celsius elevation will lead to decrease in muscle spasm, decrease the pain, and increase the blood flow. 3 to 4 Celsius elevation, which is a rigorous elevation of temperature, while 2 Celsius is a moderate elevation, while 1 Celsius is a mild elevation. 3 to 4 Celsius will cause limitation of chronic inflammation and elongation of soft tissue. So according what is the therapeutic effect that you need from ultrasound, you will substitute in T, which is the temperature. You need to elevate the tissue B by 1 or 2 or 3 to 4. If you need a non-thermal effect, you can substitute by 0.5. A here is standing for absorption coefficient. Not attenuation coefficient as we did to calculate intensity. And you must first know what frequency you have. Are you using 1 MHz frequency or 3 MHz frequency? Because attenuation and absorption coefficient depend on frequencies. So to substitute here, you must first know what frequency you use, then take the attenuation coefficient of this frequency. Finally, intensity here is standing for intensity at the lesion site. And this depends on the stage of the lesion. This is acute stage, you will choose from 0.1 to 0.2. This subacute will range from 0.3 to 0.5. Is it chronic, you will choose from 0.5 to 1 watt per centimeter square. By substituting here, you will get the time in second, divide this time by 60, you will get the time per minute. And the time which will appear to you is the time that needed to expose the ultrasound device to the lesion site to obtain the optimal therapeutic effect. This was the first factor. Second factor depends on the relationship of the lesion area to the effective radiating area. If this is the lesion area and this is the effective radiating area, you will notice here the lesion area is double the effective radiating area. So we will expose first the first part of the lesion area, which is here, by the time of exposure of the lesion site. Then after finishing, you will go to the second part and expose this area too by the time of exposure of ultrasound of the lesion site. This will lead to increasing the time of the session. So if the lesion area is equal to the effective radiating area, you substitute here in this part by 1. If the lesion area is double the effective radiating area, you substitute here by 2. If the lesion area is triple the effective radiating area, you substitute here by 3. So according what is the relation of the lesion to the effective radiating area, you substitute this part. And this requires you to calculate the size of the effective radiating area and the size of the lesion to know how is the difference between them. Finally, the last part is the duty factor. Duty factor is the percentage of the time that the ultrasound will be on during the session. There are 2 types of duty factor. First is continuous, which means that the whole session, the ultrasound will be producing during the session, and we use this in chronic stages. In the pulse type, this means that sometimes during session time, the ultrasound will be off, no producing ultrasound. Since I must give the lesion type all this time to obtain the optimal therapeutic effect, so since some parts of the time during session will be off the ultrasound, so this means that I have to increase the session time so that all this time is provided to the tissue. In pulsed mode, we have 1 to 1, 1 to 2, and 1 to 3, and 1 to 4. We choose them according to the stage of the lesion. 1 to 4 is acute cases, and 1 to 1 to chronic cases. 1 to 1 means that for each 2 seconds, 1 second will be ultrasound is on, and the other second ultrasound will be off. 1-4 means that for each 1 second, the ultrasound will be on. 4 seconds, the ultrasound will be off. So to obtain full time exposure of the lesion to ultrasound, plus using this mode of on and off ultrasound to avoid the thermal effect of ultrasound, we will calculate, we will sum the ratio, and we will multiply this ratio by the time of exposure of ultrasound to other lesion of the site. For example, if I did this equation and the time calculated is 2 minutes, and my effective radiating area to the lesion area is equal to 1, so I will multiply by 1. And since it is acute case, so I will choose a pulse mode, and it is very acute, so I choose 1/4 ratio. So I will sum these 2 ratios, which will equal be 5. Then I will put 5 in the duty factor part. Then I'll multiply all these numbers, and the result will be 10 minutes. 10 minutes is the whole session time, which will include only 2 minutes, which is time of exposure of ultrasound to the lesion site, and only 8 minutes, which is time off to avoid the thermal effect of ultrasound. This was explanation of how to use ultrasound parameters. The next lecture is going to be about laser. If you have any question, write in the comments and I will try to reply to it immediately. Thanks for watching.